This is an introduction to statistical hypothesis testing, and in this lecture we'll have a look at the basic ideas behind hypothesis testing and some of the basic definitions that we use. A hypothesis is just in general a conjecture or an idea which you would like to test. And I think one of the nicest introduction to the idea behind hypothesis and hypothesis testing is something that's often denoted by the philosopher's beans. Not sure about the origin of this. I found it on Wikipedia, and it goes like this. Few beans of this handful are white. Most beans in this bag are white. Therefore, probably these beans were taken from another bag. So the idea here is that I can formulate an hypothesis. And the hypothesis in this case is that the beans were taken from the bag. So you have to imagine this bag of beans as being well mixed. It contains white beans and some other beans, let's just say black beans. And most of the beans are white. Now I have a handful of beans. Most of these are not white. Is it possible that I actually took these beans from the bag? Yes, it is possible. But the point is that it's unlikely. If the bag is well mixed, then the proportion of white beans in my hand should correspond at least closely to the proportion of white beans in the bag. So we have a hypothesis. The beans were taken from the bag. We have data or an observation, and we have a conclusion. We say that we reject the hypothesis. Based on the data, based on the observation, based on fact, we reject the hypothesis. Note that it doesn't mean that we can say that the hypothesis is definitely wrong. All we can say is that it's probably wrong. A step up from this example into a more formalized theory of hypothesis testing is the lady tasting tea experiment, which was devised by one of the most famous statisticians, Ronald Fisher. The idea behind this story is that there is this lady and she claims that she can tell if you poured the milk first and then the tea, or if you poured the tea first and then the milk. So Fisher devised an experiment based on this where he poured 8 cups of tea and 4 each. So 4 of them had milk first and 4 of them had the tea poured first. He asked the lady to determine which cups were which. The null hypothesis, we'll get to that later, but just the hypothesis in this case was that the lady has no such ability. You can actually prove using combinatorics that if you have 8 cups like this and you randomly pick 4 and say that these 4 are the ones where you pour the milk first, for example, then you might get lucky. Just by pure chance, you might actually pick out the 4 correct cups. So with absolutely no ability of selecting, that is just by randomly selecting 4 cups, the probability that you will get all of them right is actually 1.4% or 1 out of 70. There is a Wikipedia article which describes precisely how to get to this number, as well as many other discussions of this lady drink tasting tea experiment. Since this probability is fairly small, Fisher designed the experiment such that he would reject the hypothesis if the lady got them all right. The idea here is that if she gets them, all of them correct, if she correctly identifies the four where the milk has been poured first, it's definitely not a proof that the hypothesis is false. She could just be lucky, but since this probability is fairly small, we're willing to risk that and say that the hypothesis is false if she gets them. So you can see the connection to the philosopher's beans problem. In both cases, we state an hypothesis. The beans were taken from the bag, or the lady has no such ability. We make an observation, and if, this is the key point, the observation is very unlikely to be true given the hypothesis, then we reject it. If the proportion of the white beans in the hand is very different from the bag, we reject that hypothesis. If the lady guesses all of the cups correctly, then it's very unlikely that she's guessing, and we reject that hypothesis. Also notice something really important here. The hypothesis in the lady tasting tea experiment is that she has no such ability. It's really important that we formulate the hypothesis like this. I mean, you could, in theory, formulate it as the lady has such an ability. However, that would create big difficulties. How would we in such a case calculate probabilities? If she has the ability, what's, for example, the probability of getting one cup wrong? Well, that's simply unknown, but we can calculate the probabilities based on stating the hypothesis as she has no ability, because no ability just means that we have to guess, and there is then just a 50-50 chance for each cup of getting that right. So this is a typical feature of statistical hypothesis testing. If, for example, I want to determine if there are salary inequalities between, let's say, men and women in a given sector, I would set up the null hypothesis to be there are no differences. And then I would look at my data to see if it was possible to reject this hypothesis. So here is a third example which comes closer to how we apply hypothesis testing in econometrics. So consider the following example. I have a random variable x. This random variable has a known distribution. It has a normal distribution. It has an expected value of mu, and it has a variance of precisely 1. That's known. Now my hypothesis is the following. I am stating, claiming, conjecturing, whatever you like, that mu is 0. You get to observe one random drawing from this random variable. That's the game. You get to observe one random variable and base one observation from the random variable, and based on that observation you should make a claim about the hypothesis. The observation you make is that x is equal to 4. Well, let's do some decimals. 4.12 something with a lot more decimals. Now, the reasonable thing to do in this case would be to reject the hypothesis. Why? Well, it is still possible to get the number 4.12 from the normal distribution, because the normal distribution has a range which goes from minus infinity to infinity. It's just highly unlikely to get a number 4.12 from the standard normal. You can actually find the probability that you would get a random number that's 4.12 or greater. And if you calculate that, which we can do, for example, in Excel, as 1 minus, using the cumulative CDF, norm as dist, 4.12 and 1, that will give us this probability. We see that that's 0.000019 something. So it is possible to get a number which is that large. It's just incredibly unlikely. So 0.000019 something. What's much more likely in this case is that this random number is drawn from a distribution where mu is not 0, but something greater than 0. So we have assumed, and that's sort of the framing idea behind the example, that x is normal and it has a variance of 1, so it's much more likely that mu is something like 3, 4, or 5, or anything in between. What if you were to get x equal to 1.21, let's say? Well, in this case, 1.21 is not an exceptional number from the standard normal. The probability of getting 1.21 or bigger is 11%. So with this observation, we should probably decide to not reject. Let's add do not reject the hypothesis. We simply do not have enough information to claim that this hypothesis is likely false. So based on this example, we can observe one more thing, and that is we never accept hypotheses. We never say that we accept the hypothesis. The only thing we do is that we either reject it or we say that we do not reject it. If I make this observation 1.21, of course, that will not allow me to claim that yes, that I now know that mu is 0. Because there are so many other values of mu that's consistent with this observation. Mu could be 1. If mu is 1, then 1.21 is a highly credible number. It could be 2, 0.5, or lots of different values. So we cannot claim that mu is 0. All we can claim is that based on our observation, I can't at least reject the idea that mu is 0. Mu is equal to 0 might actually be true. So the last analogy I want to make is one that's often made when hypothesis testing is discussed, and that's with a courtroom trial. So we have a defendant and we need to decide whether the defendant is guilty or not. And the basic idea behind the legal system is that the defendant must be viewed as innocent until proven guilty. So the hypothesis in this case, the one the courtroom is trying to reject, is that the defendant is innocent, or the defendant is not guilty. And it's the job of the prosecution to reject this hypothesis. The prosecution must present evidence, data, which will make us reject this hypothesis. As for statistical hypothesis, even if we reject the hypothesis and we send the defendant to jail by claiming that he or she is guilty, then it's still possible that we are making an incorrect decision here, just like in all the other cases discussed. There is also this notion of not accepting the hypothesis. If the prosecution failed to present evidence allowing us to reject the hypothesis, then we cannot really claim that the defendant is not guilty. It's not really the job of the courtroom to determine or to claim that the defendant is not guilty. All we can say is that the evidence is not enough to claim that the defendant is guilty. Alright, so let's move on to some terminology. The first thing is the actual hypothesis that we set up. And this hypothesis is typically called the null hypothesis. That's the hypothesis that we try to reject using our data, and we might be successful or we might fail in that. Sometimes we have an alternative hypothesis. It's not really necessary. For example, in Fisher's way of doing hypothesis testing, you don't need to specify an alternative. In the lady tasting tea hypothesis, there is just the null hypothesis, but no real alternative. But sometimes we do have an alternative hypothesis, which is the one that we go to when we reject the null. So the courtroom trial example, you typically specify the alternative hypothesis as the defendant is guilty. So the notation then is that the null hypothesis, the one that we're focusing on, is denoted by H0, and if we have an alternative hypothesis, it's denoted by H1 or HA. The whole idea is to collect data, make observations, and try our best to reject the null hypothesis. That's the idea. So rejecting the null, if we find enough evidence against the null, then we reject it. If the beans in the hand have a proportion that's very different from the bag, we reject it. If the lady gets all of the cups correctly guessed, we reject the null that she has no ability. If our random number that we observed is really far from zero, we reject that it comes from a standard normal. And if there's plenty of evidence claiming that the defendant has committed a crime, we reject the null that he or she is innocent. If we fail to do so, say that the beans in the hand have approximately the same proportion as the bag, then we say that we do not reject the null hypothesis. But we never accept it. I mean, even though the proportion of beans in my hand is exactly the same as the proportion in the bag, that is of course by no means a proof that I got these beans from the bag. I could have gotten it from another bag with the same proportion of white beans. So never accept a null hypothesis. That's sort of built into the game. So based on this discussion, we can actually make two types of mistakes. And these mistakes or errors are called type 1 and type 2 errors. The first error we can make is if we reject a null hypothesis that is actually correct. That's the type 1 error. If we reject a true hypothesis, then we're making a type 1 error. And we just cannot eliminate these possibilities. If my null is that the random variable is standard normal and I observe 4.12 and reject the null, I could actually be wrong. It is possible to get 4.12 from the standard normal, so then I would be making a type 1 error. Similarly, if we send an innocent person to jail, then we're also making a type 1 error. The other mistake we can make is that we have a null hypothesis that's actually false, but we fail to collect enough evidence to show this. So if we fail to reject the false hypothesis, then we're making a type 2 error. If our defendant, for example, actually is guilty, so that our null hypothesis is false, but we fail in collecting evidence against the defendant and are unable to reject it, so we have to proclaim the defendant as not guilty, then we're making a type 2 error. There's a very important dissymmetry between type 1 error and type 2 error, in the sense that it's much worse to commit a type 1 error than it is to commit a type 2 error. And the courtroom trial, I think, is the nicest way of seeing that. Most people would probably consider it to be much worse to send an innocent person to jail than it would be to let a guilty person go free, if you can even compare those. Looking at the example where we draw a random number from a normal distribution, if I'm making a type 1 error, then I'm actually claiming something quite strongly. I'm saying that the null hypothesis is false. So if I'm doing that incorrectly, I'm claiming something which is false. But committing a type 2 error, I'm not really committing to anything. All I'm saying when I'm making a type 2 error is that I don't have data to reject the null hypothesis, so I don't know if it's true or false. I'm not making a very strong statement in that case. Since we are very wary about committing type 1 errors, we give that a name. So we call this the level of significance. That is the probability of committing a type 1 error. So in a statistical analysis, the probability of committing this type of error is denoted by alpha. In a courtroom trial, of course, we can't really determine alpha, but if we set up a statistical model such as the one where we draw a random number from a distribution, then it will typically be possible to actually calculate this value alpha. The probability of committing a type 2 error is typically denoted by beta. It's not as important as the alpha. In fact, it's 1 minus beta that's typically the interesting part. So beta would be the probability of not rejecting a false hypothesis. 1 minus beta would be the probability of rejecting a false hypothesis. I want that to be high, so we call that the power of the test. That is, the probability of rejecting a false hypothesis is called a power. So what we're looking for is a procedure which has a low level of significance. We rarely commit type 1 errors, but still it should have a high power. So we should be able to single out cases where the null is false. So the whole thing is then typically put into a 2x2 table where we can look at these things. So let's split this into 2x2. The first column is H0 is true. The defendant is guilty. The lady has no ability, and so on. H0 is false. The defendant is guilty. When we are faced with the hypothesis, we have to make a decision, and we can make one of two decisions. We can reject the null. Well, actually, let's put that here. We can reject the null, or we can not reject the null. If H0 is true and we do not reject it, then this is the correct. This is okay. If H0 is false and we reject it, this is also correct. This case here would be not convicting an innocent defendant, and this case down here would be convicting a guilty defendant. This one is the biggest problem. Let's call it type 1 error. We are claiming that an innocent defendant is guilty, and this is called a type 2 error. We are claiming, or rather, we don't have enough evidence to find a guilty defendant guilty. So that's the setup of hypothesis testing and the basic notation that's used.